Hey, what's going on, man? What's happening? So today we're going to be talking about. So today we're going to be talking about dependent current sources. All right, and as you can see here, we have our normal electrical drawing. But as you can see, we have this voltage source right here. We have this voltage source right here, and and we have this current source right here. As you can see, it's labeled as IO3, right? And that's basically just LT Spice's way of saying that this is a dependent current source and it's dependent on current IO and it has a gain of 3. So that means we have to multiply IO by 3, right? So what does this mean? So like why do we have like a voltage source here with the 0 volts on it and yada 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 blah blah blah. I'm about to tell you in a second. All right. So as we can see, we have the negative and positive terminal, right? Of this battery, right? We know electricity likes to travel from negative to positive, right? So it's going to go in this direction to the positive terminal, right? Because we know like electricity likes to travel from low potential to high potential, right? So that's exactly what this battery is insinuating, right? You have a 0 volt battery here that's just saying like, hey, the current is traveling in this direction. So the voltage on the battery doesn't matter because that's not what the battery is trying to convey, at least in the LT Spice anyway. That's not what it's trying to convey. It's trying to convey that the current is traveling from negative to positive in this direction, right? It's traveling from low potential to high potential in this direction, right? That's what that battery is trying to convey. Now, see, like I said, this is how LT Spice represents a dependent current source. I'm about to tell you like what a normal electrical drawing looks like. So, oh, I opened up the wrong thing. Here we go. All right, so a normal electrical drawing is going to look like this, right? So as you can see, we still everything is still the same. We still have our dependent current source here. Now we have uh our current is displayed as just a current. It's not displayed as a voltage source anymore. It's displayed as just a current moving in a direction. Now this direction is moving in conventional flow terms, right? Conventional flow and electron flow are basically the same thing. Like they have the same principles anyway. The only difference is in conventional flow, current travels from high potential to low potential, right? So so what this is saying is that the current is traveling from the high potential to the low potential, right? So it's still the same as if the current, like for example, we got it right here. We're traveling from low potential to high potential, right? We're traveling from low to high, right here, right? It's just in conventional current, right? It's going to be traveling from high potential to low potential, right? But it still doesn't change the fact that the high potential and the low potential are the same exact thing, right? Doesn't matter where you use conventional flow or electron flow. And let me give you an example for that. Let's say our high potential equaled 80 volts, right? And our low potential equaled 50, right? It equaled 50 volts, right? Okay, so we have a voltage difference of 30 here, right? So if we travel from 80 volts to 50 volts, we still travel from high to low, right? Now, let's say we traveled from 50 volts to 80 volts, right? Like 50 volts is still the low potential here, and 80 volts is still the high potential here, right? So the same rules apply. And we know the reason why we know this is because our equation, right? Voltage difference is going to equal high potential minus low potential. It doesn't matter what you're using. It doesn't matter if you're using conventional current or if you're using electron flow. This equation will always stay the same. High potential minus low potential, right? So I know that sounds a little bit confusing, but as we work through these problems and you do it more and more often, you will, like I said, it will start to become second nature. So let's start working on this problem. So what's the first thing we want to do? Obviously, we want to label the points we know. So let's go ahead and label ground because we know ground is going to be 0 volts. So ground is 0 volts. All right. Is there any other points we know? Doesn't look like it because, as you guys remember, the resistors. Anytime a current hits a resistor, Ohm's law has to take an effect. So this is not 0 volts. This is 0 volts, but this side is not 0 volts, right? Because there has to be a voltage difference across this resistor for electricity to be flowing through the resistor, right? So, so there's no more points. So we're just going to go ahead and label our essential node up here, and we're going to start solving. So let's do that. All right, first thing I want to do before we start solving is I want to obviously solve for our dependent current source, so that way we don't confuse ourselves down the line. So let's see, what is IO going to equal? So IO is going to equal, right? It's going to equal the high potential of 80, right? Because 80 is our high potential here. So we got to find the voltage difference across the resistor, right? We're going to do 80 minus VA, right? 80 minus VA divided by the total resistance in the wire, right? Divided by the total resistance in the wire. So we're going to have 65 divided by 65 ohms. And that's going to give us our current. And that's our current on that. So that's what IO equals. IO equals this, if I can type correctly. So IO is equal to that. That is what IO equals. Now we want to see what IO times 3 equals. So let's do that now. 0.1. Right. Let me space that out just so like it's not all clumped together. If I can even do that. There we go. All right. So we're going to have 3 IO. And that is going to be equal to what? So we got 3 times 80. That's 240. So we're going to have 240 minus what? Actually, I want to do this in fraction form. So let's do that real quick. Can 65 go into 3? I don't think it can. But let's see. Can it? No, it cannot. All right, cool. So we're going to do 240 divided by 65. That's going to be equal to 48. So we're going to have 48 over 13 minus, what is this going to be? 3 over 60, yeah. Minus VA 3 over 65. Right? That's what 3IO equals. All right. So now we can start doing the real stuff, right? So let's solve for our current in the first wire. Let's do it real quick. So we're going to do what? VA minus 80 divided by the total resistance of that wire is going to be 65. And that is our first current, right? And we're going to do VA. We're going to do the voltage difference, right? So we're going to do VA minus ground, which is 0. And we're going to divide that by the total resistance in the wire, which is 25. Okay, so we completed that wire. Then we're going to do VA, right? Oh, we don't even have to do it, right? Because we know the current. Now, let's see if there's going to be a current decrease or a current increase, right? So we're going to go through the ground, right? And then we're going to hit the current. Now, we know this is the negative terminal of the current source, and this is the positive terminal current source, right? And we know, right, it's going to be opposite from a voltage source. So, for example, here, right, we got a voltage lift of 80 volts, right? Because we went from negative to positive in a voltage source, we got a voltage lift there. But here in the current source, we're going to get a current decrease because it works opposite to the battery, right? So we're going to have a current decrease there. So we're going to do minus, right? We're going to do minus, and that's IO3. So we got to write IO3. So we're going to do 48 divided by 13 minus VA 3 over 65, right? And all of that should be equal to 0. Now all we got to do is simplify. Let me make sure I'm doing good on time here. Yep, we are. Okay, let's go. 2.0. All right, let's simplify. So we're going to have VA minus 80 divided by, well, hold on, my bad. We're going to have VA over 65, VA over 25, and VA over 65. Or VA 3 over 65. So let's see what goes into all those numbers. So we know 5 can, right? So let's do that real quick. So 5 can go into 65 how many times? 65 divided by 5. Can go in at 13 times. So let's write that. We got 13. I'm sure we're going to have two 13s. We're going to have 5 and 13. So 13 squared times 5. So they can all go in at 845. Is that true? 845 divided by 25. No, it can't. Okay, so never mind. So we only have 113. So we're gonna have 13 times 5. So they can both wait. 25 can go into 65. No, it can't. Hold on. Let me pause the video real quick. Okay, I see what I did wrong. All right, so we're gonna have 5 squared. I did 13 squared. We're gonna have 5 squared times 13. Yeah, that's gonna give us 325. 325 can go into all those numbers. So 325 divided by 65. That's gonna be 5. So we're gonna have 5. We're gonna have 5. Let's write that. Actually, I want to keep that there just in case. All right, so we're gonna have 5 v positive VA 5 over 325, right? That's going to be our base. All right, so we're going to have 325. And then we're going to do 325 divided by 25. It's going to be 13. So we're going to have 18 right here. And then we're going to subtract. No, we're not subtracting. We're adding that too. Okay, that's crazy. And what is that? What is 325 divided by 65? It's going to be 5. So we multiply 5 into 3. And what is that going to be? That's 3, that's 15. So 15 plus 8. 15 plus 18 is going to be 33. So we got 33 over 325 is 33. 33 over 325. Can that simplify anymore? No, that cannot. All right, cool. And that's going to be equal to what? Do we have any numbers? We have 2 numbers. We have 80, negative 80. Okay, yeah, so both of them are negative. Okay, cool. So what can go into 13 and 65? Well, 13 is a prime number, so nothing can go into that. So we're just going to do 5 again. So we're going to have 13 times 5. 13 times 5 is 65. Okay, they can both go into 65. Yeah. So we're going to have, what is this? 48 times 5. So we're going to have 48 times 5, which is 240. So we're going to have 240 plus 80. 240 plus 80. Ah, shit. 240 plus 80 is going to be 320. So we have 320 over 65. What does that simplify? That's 64 over 13. So we're going to have 64 over 13 here. Okay. And we're going to make that positive. Now we can solve for our answer. So let's do that. So we're going to have 3.0. Let me just make sure how much time I got left. Okay, we're good. We should be able to finish this. All right, so we're going to have 33 over 325. Well, my bad. 325 over 33 times 64 over 13. That is going to give us 48.4. So we think VA is going to be equal to 48.48 according to our calculations. So let us see if that is correct. So let's run a simulation. Here we go, 1 second. And that is correct. As you can see, that is indeed correct. All right.